In a modern city, every lit window and pulsing server depends on a very specific set of 17 ingredients. They are the invisible foundation of the digital world. These electric vehicles rely on high-performance magnets inside their motors. Without the rare earth elements used to build them, these high-efficiency engines simply don't function. That same reliance exists here. Ballistic missiles use these 17 elements in their guidance systems. There are no known substitutes offering the same magnetic strength. Because these elements have no viable alternatives in high-end manufacturing, any interruption to their production stops the assembly lines for both civilian technology and national defense. Mining usually implies a search for concentration, finding a dense vein of gold or silver trapped in a seam of rock. Rare earths are different. They are actually abundant throughout the Earth's crust, but they are scattered thinly.
They almost never cluster in the large, pure nuggets that traditional miners look for. Getting them out requires a total deconstruction of the crust, processing thousands of tons of earth just to find the trace amounts hidden within. The process begins with massive physical scale. Giant excavators tear into the landscape, carving out open-pit mines to reach the deep layers where these elements reside. The primary target for these machines is carbonatite. This igneous rock is the most common host for the specific minerals that contain rare earths. To find the usable ore, mining teams have to blast, excavate, and haul away millions of tons of this solid carbonatite crust. This crystal, bastnasite, is what they're looking for. It holds the elements we need, but it's physically fused to the surrounding gray rock. Separating that crystal from the rock requires pulverizing these massive boulders into a fine, workable dust. After moving literal mountains, you are left with a gray, powdery mixture. The elements are still there, but they are now microscopic and hopelessly tangled together. At this scale, the problem becomes molecular. These 17 elements are chemically sticky. They share similar properties and bond tightly to one another. To break those tight bonds, the dust is submerged in massive leaching tanks filled with bubbling, toxic acid. This diagram shows the process. Acid dissolves the dust into a liquid solution, allowing elements to separate from their hosts. Because they're chemically similar, this repeats. The solution flows through hundreds of vats, each stage stripping away specific impurities. This is how you isolate a single target, like neodymium, from its tightly bonded chemical siblings, like dysprosium. This requires workers to operate in an environment of constant chemical exposure, managing highly toxic baths day and night to keep the separation moving. The difficulty of rare earths lies in this transition from the heavy machinery of the mine to the precision and hazard of the chemical lab. Once the chemical separation is complete, the result is pure, isolated metals, ready for the factory. These metals are then shipped to clean rooms like this one, where they are manufactured into delicate processors running our devices. Our most advanced, clean technologies are only possible because of the toxic, heavy industrial separation that happens miles away at the mine. This total dependence on such a specialized and hazardous process creates a structural vulnerability in how the world builds technology. Because chemical separation at this scale is so toxic and specialized, very few places on the planet are actually equipped to handle the massive waste and the complexity of the process. This creates a global bottleneck. If a single provider dominates the chemical processing stage, they control the flow of finished materials to every other manufacturer on Earth. The nations or entities willing to manage the environmental and chemical costs of this separation end up holding significant leverage over the global high-tech supply chain.